Hi, I'm Chris Brown. This is lecture 2.18 in axiomatic design and manufacturing processes. So for the next few minutes, I'm going to be talking about cost calculation in machining. So optimizing cost per cut, or could refer to different kinds of operation with a small change in the variables. This is important, and being able to account for what it costs to perform a manufacturing process is important. And if you can't calculate the cost well, that companies can fail because of that. Cheaper, from the point of view of, say, a cheaper tool, is not always less costly because it can lead to other costs. And it's interesting that you can pay actually more than twice as much for a tool that lasts exactly twice as long and still save money because you save in the tool changing cost. So that's something we need to be able to account for. Now, in terms of axiomatic design, cost is usually a constraint because it is coupled. And so it cannot be adjusted independently. It depends on the FRs. So when we have something that, when we can decouple things, we don't have to optimize. But for cost then, because it is coupled, we have to optimize. And so the question is, since the cost or the tool life, as we saw in the last lecture, is related to the cutting speed, how do we get the best cutting speed to give us the least cost overall? All right, so that's what we're going to look at. Now, profit rate, and some people say you want to maximize profit rate. Now we know from Thompson's 2013 ICAD paper, maximize is probably not is not a good FR, and we can kind of see why here. Because in order to maximize this, the value would have to go to some high value, say infinity even, and the cost would need to go to zero, and the time would go to zero. So what high value do we pick for the cost? How can we, we obviously can't go to infinity, but how do we know we've got to the maximum value? And there's actually probably just a target value that we really need in order to have the market share that we want for some particular product. So the value of the maximized profit rate has appeared in the literature as an FR, but it probably should be provide a sufficient profit rate or provide sufficient profit rate. All right. So how do we decompose cost per cut? So we're going to go through another decomposition so that we can sort of solve the problem. So here is one decomposition of this. So CN, so you get cost per cut divided into 5 different components. So CN, the first one, are non-productive costs. Those are things that don't do anything. The cost of cutting, that's the part that's providing the value. That's the CC. Then we have the cost of changing tools. I suppose you could argue that's another kind of non-productive cost, but we're going to keep it separate. The cost of the tool itself, and then the cost of the raw material. So, at least for an example, let's decide that this is a collectively exhaustive, mutually exclusive decomposition that gives us a minimum number of things to consider for the cost per cut or the cost per operation. So if we want to minimize this cost with respect to speed, in the cases where increasing speed means decreasing, say, life. This is similar actually to a problem driving a car. As you increase the speed above a certain point, your gas mileage starts going down, but your time to arrival goes down as well. So, and that's worth something. So how do you handle this? So what we need to be able to do is put the cost per cut as a function of cutting speed, and then we can do a max-min type problem. We can take the derivative and set it to 0. So how do we sort out then which ones of these are going to be factors of cutting speed? Well, the non-productive cost, this is directly associated with the operation, but no cutting is taking place, so it's not going to have an impact probably. So this doesn't change with cutting speed. So this is equal to some time and some cost per, so x is some cost per time. Say the operator in the machine is appropriate. This italicized t is the time, like the initial setup time, for example. The cost of cutting. So this is equal to the cost of the cost per time for the operator in the machine. Time is appropriate. Now you put that down there as appropriate because you can have unattended cutting operations. So you don't always need the operator there, but all right, so you can work it out. The cost, this is the cost of the actual cut. This is the value added process. So the cutting speed is here. It reduces the cutting time. So T sub C is going to be the time to complete the cut or the operation if we're looking at some other thing. So T sub C is equal to the distance that the tool must cover divided by the speed at which it's covering it, essentially. So this is a simple kind of distance, time, speed problem. So then CC is going to be equal to the cost per time times the cutting distance divided by the cutting speed. So there is where the time comes in. So we've just made a substitution there. So cost of changing tools, that's CH. So we need to change a tool when the tool wears out. So what fraction of the tool life is allocated to one cut? So we get TC divided by T, where T is the tool life, a function of the cutting speed. TH is the tool changing time, and X, again, is the cost of the time the operator in the machine is appropriate. So you might have a robot, for example, changing the tools. All right, so CT is the cost of the tool per cut. So again, we have this ratio of the time for the cut divided by the tool life. Now it's multiplied times Y, which is the cost of the tool. So, and the tool life we know to be a function of speed, as is the cutting time. All right, so what terms are functions of speed? So CW is the cost of the raw materials, and like Cn is not a function of speed, so we'll eliminate those two. And that leaves us with the cutting time, the tool changing time, and the cost of the tool. All are going to vary with cutting speed. So we need to rearrange here and make some substitutions. So first, here we've substituted in the different things that are a function of speed. We can take out now the tool life, but we need to put that in terms of speed, so that's the distance traveled divided by the speed. So now we have an equation here where we've got the tool changing time divided by the tool life, and we've got the cost per tool divided by the tool life. So to find the tool life as a function of cutting speed, V, then we need to substitute and then differentiate with respect to V. All right, so when we substitute, how do we get tool life as a function of speed? Well, we go to the Taylor equation, and so then we use that. And here we can see the Taylor coefficients coming in as we make that substitution in the tool life. So now you can see we've got a number of terms that involve the cutting speed, and here's the cost of the machine per operator. So, excuse me. So we can see what the speed is going to do. So here we have, as we the cost due to cutting goes down as the speed goes up. The cost due to tool changing and tool time goes up as the speed goes up. And the total has a minimum cost associated with it. So there actually is a minimum. So if we had an FR for minimized tool cost, we would say, all right, let's do use the Taylor equation and the machining variables, and we can actually determine the minimum cost. Now, in practice, this isn't used very much, interestingly enough. It would seem like a good idea to use it. Anyway, so here's the way the derivative goes. Now, one of the reasons why this isn't used, and here's the expression, this is the speed, actually, and let's take a look at this. This is the speed for minimum cost. So it's a function of the Taylor coefficients. There we have n and c. There's n again. It's also a function of the cost of the tool and the labor. And the tool change, the time and the cost of the tool. So that the more... so anyway, so these have some... these all have some impact on what the best speed is. So it would seem like that might be a good thing to do, to use that. But in practice, actually, nobody does. In practice, it works out that aluminum now, as long as it's a forging and not a cast aluminum that might have some sand or abrasive mixed in, you just machine as fast as you can. And the effect of the aluminum on the tool isn't that important. So you don't have to worry about the effect of speed. Although machining steel or titanium, that does become important. So as I was saying, in practice, the optimization is never used. And part of the problem is that it's specific to the feed, speed, depth of cut that you're using. And so, and how you've set things up, and the coolant, and so forth. So people tend not to use this. And people tend not to report the Taylor coefficients because they're so dependent on the situation. But there's enough intelligence now, or they're connected to enough intelligence, the CNC tools, so that if they were properly programmed and instrumented, they could calculate the optimum speed themselves in large production runs by varying the speed a little bit and looking to see what happens to the tool wear, and then developing the whole thing. You could program a machine to do that all on its own. The problem is, too, though, that machine has to be sort of in sync with the rest of the production line. And so this might have an adverse effect on line balancing. However, it's still a possibility. Something could be done. So the optimization, as I was saying, is necessary when systems cannot be decoupled. Also, optimization is good for dealing with constraints or OCs or SCs, like things like the cost, selection criteria, optimization criteria. Great. Thank you very much for your attention.